Thank you, Tom, for the introduction. All right, so today we talk about fusion. So I phrased this talk with a question. So can fusion step up? And lots of people have lots of opinions about this. So I'll try to give this talk, and hopefully at the end of the talk, I will convince you that this is a very interesting research area with lots of need for young scientists to help this field along. So there are encouraging developments just recently in laser fusion research, and let's see if there's enough momentum now to really develop a laboratory fusion source and maybe even help with future energy needs. So let me introduce first the world energy supply. So we'll talk about the terawatt challenge, meaning I will try to introduce to you the scale of the problem that we're trying to deal with. Then we talk briefly about the wait and see strategy and where that leads us to. And then we look at the recent developments that are happening at Lawrence Livermore Lab, namely laser-driven fusion research at the National Ignition Facility, where I worked for 18 years. So I will talk about the beginning, where I was a key player, and recent successes that we have been introduced just recently, and I think may point towards a more bright future. So this directly leads into a fusion energy science program that we're currently leading here at Stanford. We use LCLS, which is a unique tool to make new discovery science or progress in discovery science. And we will talk about some novel X-ray scattering experiments that we have done. And particularly, they have helped us to determine the physical properties of matter in extreme conditions. And I will show you that these type of research, this type of progress is exactly needed for development of fusion energy. All right, so hopefully at the end, I will have convinced you that progress has been made and more progress is actually needed and it's actually important for the future of all of us. All right, so let's talk about the terawatt challenge. So here's several examples of products that need energy or power. So I converted everything to a power unit. So that's our Macintosh laptop. If you use a couple of watts to run it in steady state. If you use a toaster or a coffee maker, you're already talking about kilowatts, a couple of kilowatts to run it. This is a Eurostar. It needs 10 megawatts to run. Of course, much of this energy that we are using is produced by power plants. Typical nuclear power plants give out a few gigawatts. But in order to power the planet, we need terawatts of power. In fact, we need tens of terawatts of power, and it's projected that in the near future we need to go to 28 terawatt, namely by 2050. So let's look at the world energy consumption. So where is all this power coming from? So we know, and most of us know, that most of the power is coming from oil, gas, and coal. And when I was entering this field, that was in the early 90s, and actually during the 90s, things actually looked pretty well. I mean, oil was leveling off, coal was leveling off. To some extent, even gas was kind of taking a little break here. Hydro was growing up nicely, nuclear was leveling off, and actually renewables just came online. So there was lots of hope and lots of momentum that energy can be solved. Just recently, as you've seen, coal is taking off a lot, and all the CO2 emitting energy sources have really come back and taking over. So why is that? Of course, when you look at the production costs of electricity, if you look into the United States, there's numbers from 2002. We can look at more recent numbers. They haven't changed much, but the bottom line is really coal is the cheapest you can do in order to produce electricity. Of course, gas and oil, wind and nuclear are somewhat competitive, but solar is really out there being very expensive. So coal is the cheapest and the most abundant one. We know we have reserves. There's estimates vary all over when you look on the internet, but we are very confident we have at least 200 years, maybe even 2,000 years of coal. And so in principle, we could get going. However, where does that lead to? Coal is today's solution of the growing energy demand. You can see it here in China. Coal is almost tripled now. Some countries are holding back, like the United States, Germany, but others like India is also doubling its coal production. And of course, it comes with all the bad stuff. It comes with mine disasters, which is just 2 days old, and of course with CO2 emission that is really causing now big problems. And this is shown here. So we are approaching the trillion ton threshold. What this means is researchers that work on climate change have set out a goal that we should the total cumulative CO2 emission into our atmosphere should be held below a trillion ton in order to limit global warming to 2 degrees. And when you look at all this, you can see that the United States is not doing too poorly at this. You know, at a cumulative CO2 emission, or like particular countries like the UK or Germany are pretty much having now a constant emission, but other nations, particularly China and as I showed India, are just taking off. The energy demand is just growing, and coal is the one that is being is the energy of choice. So let's look at an example. So why is Germany actually keeping it constant? So coal here is about flat or just slightly rising. And what happened in 2000, 6.3% of the energy was renewable. So right now, in 2012, 25% of the energy was renewable, which is hailed as a big success. So you can read up in the internet, most people think this is a really great thing that has happened. However, the costs were enormous. So it's $100 billion per year in surcharges. So the electricity in Germany costs twice as much as in France, which is mostly nuclear. Then, in addition to that, there's a $70 billion export loss because of the high energy cost. So the question is, can this be a global model? And the answer to that, you have seen on the previous slide, the answer is no. You see, other nations are going to coal. They cannot simply not afford this type of a hit on their economy. So, and of course, the consequences are well known, they're well felt. I mean, there's lots of talk on the radio, you've all seen it. All our glaciers are melting. Here in this case, in the Alps, the glaciers are almost completely gone, not visible anymore. And of course, storms are, this is of course a Photoshop, but these are the storms that have hit the Gulf Coast over the last couple of years. And the storm intensity are just increasing. So in order to be serious about global warming, in order to be serious about climate change, it is mandatory to come up with non-CO2 producing energies and to limit our CO2 emission into the atmosphere. So with all the introduction, of course, what about fusion? Nuclear fusion is a widely accepted source of energy that could play a big role in the future. So why is that? So it has abundant and efficient limited fuel supply. So 1 out of 6,500 atoms is deuterium. You can find in the ocean, there's plenty of fuel around. It's inherently safe. There's no runaway or low residual heat, and I'll show you later on a fusion target, which was shot at the National Ignition Facility. It looks like this. And the fusion plant, however type it is, whether it's laser fusion or magnetic fusion, will always burn only a few minutes of supply at a time. So there are no runaway reactions. There's never enough fuel around to produce any harm or any danger to the facility or to people around. So in this case, the nuclear fuel is actually in this small little layer sitting here on the inside that you can hardly see. And it's deuterium-tritium, and in this case it's 0.17 milligrams of nuclear fuel. And that's the fuel that will be put into a device for a fusion experiment. All right, so of course fusion is great for energy security. You have all seen what's going on in Eastern Europe with the Ukraine and the Crimea. And of course energy dependence is a big player in all these negotiations and reactions by politicians. As you know, there's countries around Russia are 100% dependent on the natural gas supply from Russia. Ukraine itself is 66% and Germany is 36%. And of course, if you go farther away to France, they only get 40% of their energy from natural gas from Russia because they're mostly independent through nuclear power. So by having energy available for the nations, that component will be taken away as a negotiation point, or as a point where people can put pressure on nations. All right, so if fusion was to happen, people believe it is scalable to meet demand. This is one of the biggest fusion experiments in the world that are right now being built. This is the ITER site in the Provence in France. And you can see it is quite big, but it doesn't take away too much land. And people believe with efficient land use, one can build enough power plants to power nations. All right, we all know there will be a low environmental impact. There is no greenhouse emission, of course. And when you look at this plot, which is the binding energy per nucleus, which is MeV per nucleus, once you start to produce fusion processes, you bring the deuterium and tritium together, and you produce helium particles. So there's a big energy gain, nuclear energy gain. So there's no carbon involved in this process. And it's in fact the biggest output per reaction of any fuel around. So that's naturally the choice of nature. This is the process that fuels us, that powers the sun. Other process, nuclear fission, is here on the right-hand side, and you can see it's actually much less effective than nuclear fusion. And finally, there's no high-level toxic waste in fusion. I suppose that's very different, of course, from nuclear fission. And we believe that with the development of a fusion energy source, angry protests like this will be an event of the past. Having said all this, how does the big picture look like? So what needs to happen? We need to produce targets, and lots of targets. Those targets will be inserted in the center of a big target chamber, sitting here. And then one uses a laser driver or a particle driver to create a fusion process. The fusion process then produces neutrons. The neutrons interact with a lithium blanket, which sits on the inside of the target chamber. And it transfers heat to a heat exchanger, and then you power turbines, and you put energy or power into the net. And of course, the fuel cycle needs to close. That means the residual material will melt, it will be recollected at the bottom of the chamber, it will be fed back into target fabrication, and will be reinserted into the target chamber to keep the process running roughly at a frequency of 10 Hertz or so. So a power plant will fire roughly 10 targets per second to produce 1 gigawatt of electricity, and that would be needed to power a major city such as San Francisco. So here's the fusion power cycle in numbers. So in order to get a gigawatt out, we actually have to produce 1.3 gigawatts. So then that allows us to put 0.3 gigawatts or 300 megawatt back into our fusion cycle. That will go to feed our driver. If we can build a driver that is 10% efficient, we have 0.03 gigawatts or 30 megawatts. That means 3 megajoule of energy will be available at a rate of 10 hertz. So now you have this 3 megajoule of energy with which you can do things. And what you do, you drive a target. And that target must produce gains through fusion. And the gain must be of order 100. Some people believe it should be 66, some people 50, but it must be of that, somewhere in that ballpark. If that happens, out of 0.03 gigawatts, we are back to 3 gigawatts. And these 3 gigawatts then go to our reactor and to our turbines. With an efficiency of 43%, we are back to 1.3 gigawatts. So the key in all this, and I believe the key to convince anybody that this has legs, is a target gain of 100. So how do we get there? How can we produce large gain in a fusion event? So fusion requires high temperatures. So what this means is you bring a deuterium and tritium close together. If the temperature is high enough, they're going to get close enough to overcome the Coulomb repulsion. So you fuse deuterium and tritium. What you do, you produce an alpha particle and a neutron, a 14.1 MeV neutron. The way it works, first you compress material that heats it up. You create a hotspot where fusion starts to set in. The goal of the hotspot is to actually, it must be dense enough to keep the alpha particles in the hotspot. That means the alpha particle energy of 3.5 MeV will stay in the hotspot and heat the hotspot further. The hotspot gets so hot eventually that the surrounding fuel also gets ignited. And then you have a full propagating burn wave that goes through the main fuel and produces energy through fusion. So how does this work? This is a DT, this is a schematic of a DT implosion, a capsule. You have an ablator on the other sides. The ablator absorbs energy, it explodes away, and the rest of the capsule is imploding. And what you got the DT fuel on the inside, DT gas in the middle, and you're imploding your fusion capsule to a diameter less than a human hair. So you produce truly a microscopic star in the laboratory. So why do you compress material? Because you want to have high areal densities. That means high rho R. Why is that important? Here's the density of our deuterium-tritium plasma. Liquid density is roughly 0.1. So in order to stop alpha particles, you then have to have a very large radius so that you have enough stopping and keeps the heat in our plasma. So in this case, the radius must be like 30 centimeters. Which means there's a lot of DT fuel. And indeed, if you would burn all of this, you would have 300 kiloton explosion. This cannot be contained. That's like a nuclear bomb. So what people want to do, they want to go to very high densities, namely 1,000 gram per cc, which is like 50 times compressed lead, or in this case, 1,000 times compressed hydrogen. And now you only need like 30 microns in order to stop the alphas. And you get, in this case, 12 megajoule of yield, and that can be easily contained. In fact, this is close to where you want to be. But maybe a little bit more would be better, but this is like the ballpark and would be called a big success if you could get there the next few years. So besides stopping alpha particles and to heat the hotspot further or the plasma further, high area densities are also important because they determine how much fuel is actually being burned. That means the denser the material is, as you start burning, it doesn't fly apart easily. It's called inertial confinement. And for that reason, the denser it is, the more you burn. So you can count on burning roughly 10 to 30% of the fuel that you can assemble around a hotspot plasma. So then there's one other trick. So this looks like a ball. Of course, it's not a ball. It's much better to have a hollow sphere. Because if you were to volumetrically heat a ball of DT, one would need to put 130 kilojoule into this fuel in order to heat it up. And that means a driver must be of order 10 megajoule or maybe even higher. So in this case, the mass sits on the outside. And now there's less mass overall to heat up. So now you only need like 10 kilojoule roughly of energy that needs to go into the fuel. And a driver of a megajoule, and mainly most experiments may show that this was of course somewhat optimistic, but it's at least, it catches the right order of magnitude. So, and then what do? You create a hotspot with dense fuel around. So the hotspot is characterized by a high temperature in the middle, but low density, confined by a dense layer of fuel surrounding the hotspot. So do the numbers work out? Yes, of course they do, because if you keep the material close to Fermi degenerate and compress it, we can calculate how much energy we need. We need 10 to the 7 joules per gram in order to compress the deuterium. However, we would get 3.4 times 10 to the 11 joules per gram from DT fusion. That means the compressed energy is much smaller than we would actually get out if we burn the DT. So this is the energy we need to put in to compress it. So let's equate it with 1/2 mv squared and have a factor of 2 of ignition margin. What we find is if you want to go to rho of 10 to the 3, that means 1,000 grams per cc, we need to implode our capsule with a velocity of 360 kilometers per second. That's a fast implosion. So we can go through a 3-dimensional rocket equation, and that tells us that the exhaust on the outside, in order to make the inside go at 360 kilometers, the exhaust must be 120 kilometers per second. In order to create such big ablation velocities, we need a pressure on the capsule of 100 megabar. And 100 megabar pressure can be achieved if the capsule is inside of a radiation can or radiation environment. We call it a hole with a temperature of 300 eV. So now remember, the surface of the sun has a radiation temperature corresponding to 6,000 degrees Kelvin. So this is a hot plasma, a hot target that is responsible for compressing the fusion capsule. So 1 eV is 11,605 degrees Kelvin. All right, so then here's a calculation of what will happen. We're compressing the capsule. You're compressing more and more. Alpha heating starts to set in as the area density goes up. And at stagnation, alpha heating actually starts to kick off. And now what that means is a nuclear burn wave is launched into the fuel around. Temperatures go to 50 kiloelectron-volt at peak burn, and then the system disassembles. Of course, the goal is to produce a microscopic star on Earth. The goal is to recreate the sun on a micron scale length of 30 to 50 microns. So let's talk about high energy density science conditions. So where are we in the pressure scale? So a hydrogen molecule, the binding energy is 10 to the 11 joules per meter squared, which is roughly a megabar. If you go to the center of Jupiter, we find pressures of roughly 80 megabar. This is roughly the pressure you need on the outside of the capsule to implode. If you look into the center of the sun, the temperature and densities are such that the pressure is 300 gigabar. That's where we need to be in order to set off an igniting fusion capsule. And I will show you later data that pressures right now are approaching these conditions but are not quite there. Once the ignition process starts to happen, the pressure in a fully burning system would actually vastly exceed the central pressure in the sun. So for that reason, in order to accomplish these pressure regimes and to demonstrate the nuclear burn process, people have built the National Ignition Facility at the Lawrence Livermore National Laboratory, which is a big laser. It's like 3 football stadium size. But as you can tell from my accent, I grew up in Germany, so we sing in soccer fields. So it's a big stadium-sized facility, and you want to put all the laser energy in here into a small volume, namely a centimeter-sized hole round. So this is true high-energy density science. That means all the laser stuff goes in here. So of course, the goal is to get matter temperature of 10 to the 8 Kelvin, radiation temperatures of 300 eV, I told you earlier, 1,000 gram PCCs, and many 100 gigabar of pressure. All right, so how does that work? So let me see if that movie runs. So this is actually a movie from a system shot at NIF. So this is the control room. The shot director sits here and, oh, maybe I shouldn't have done that. Let's try that again. So apparently it doesn't like me to use my laser pointer while the movie runs. So the shot director sits on the left. So he's counting down for the system shot. But first thing that is going to happen is the capacitors are being energized. That means you see that here. And they're loading up the flashlights. So now they have a fiber optics laser that is producing temporarily shaped pulses at a nanojoule level. They are feeding the big laser system that sits on either side. And now you have also spatially shaped the lasers to extract the maximum amount of energy that is being stored in the glass laser system. So now those laser beams are propagating through the laser chain, and they're going through a spatial filter, and now they go through a 4-pass. And what is lighting up in this nice pink color, that's a laser glass through which the laser beams are being amplified. Each single laser is more energetic than any other laser facility in the world. And there are 192 of these laser beams. So now they're all propagating towards the target chamber. The first go to the switchyard, where they're being distributed in an up-down geometry. And then they're being transported over to the target chamber. And they're You can see the final turning mirrors. They now go towards the target chamber center. They get frequency converted first to the green, then to the blue. Focus on target to a focus spot size of roughly 1 millimeter. And they go to the inside of a hole worm. In this case, it's a gold hole worm. Some experiments I also have done with depleted uranium. And in a few billions of seconds, the hole worm walls are being heated up by the laser beam, producing an ablation pressure on the fusion capsule of 100 megabar. Now, the outer part of the capsule is exploding, but the DT fusion on the inside, the DT fusion material inside is compressed, creating a peak burn, many 100 gigabar of pressure and fusion energy. So here's how a target looks like. So this is actually being shot. So those are research targets. So this is not a target that you would have in the end in a fusion facility, but in order to, so each single one is a prototype. It costs a lot of money to build a single one, but each single one also serves a different need to study the physics processes that are going on in your experiment. So this is about 1 centimeter in length, half a centimeter diameter. And there's a fuel line here that fills the capsule. There's a fuel line that fills the hole worm. And you can actually observe the capsule that I've seen you earlier through a starburst pattern that is cut in the side of the hole worm. And you see the DT sitting right here on the inside of the fusion capsule. So this is in a fully cryogenic target. That means DT is all ice and is filled in a liquid mode. So in order to protect your system, there's a shroud around it. Just before you shoot, you open the shroud, and then the laser shot will happen. And of course, you've published the early results on fielding DT implosions on NIF in a plasma physics journal. It was the most downloaded paper ever for this journal. All right, and of course, the first implosions were very successful. We actually got round implosions going. And here's how an experiment looks like. In this X-ray eyes, you see the laser beams irradiating the inside of the hole worm, producing the X-rays, then pinching on the fusion capsule. And actually, you can see in this camera a little dot, and that dot is indeed the imploding capsule. See, this is a round implosion. So this is a gated microchannel plate detector image, 9 kilovolt. You can see that the initial capsule diameter was 2.2 millimeter and has been compressed to less than 50 microns. So this is the emitting region is 50 times smaller than the initial capsule diameter. And this actually shows fairly good symmetry. And of course, we also had a neutron detector. One can also look at where the neutrons are coming from. And again, it's a fairly round implosion setting up here. So now you see a nice round implosion, but how well are they actually performing? That means how close are they getting to producing enough fusion neutrons to produce alpha heating and to set up ignition and burn. So for that purpose, a whole variety of detectors and diagnostics have been commissioned and fielded at the NIF. And I just mentioned a few of them, and I tried to go through them quickly. We can discuss them later, but let me just go through them. So some of them is neutron activation to measure the absolute yield, which is important. Another one is neutron time of flight. That measures the ion temperature, which you also want to know. The magnetic recoil spectrometer measures the neutrons that come out of the capsule, but that have lost some energy from scattering in the dense shell that surrounds the hotspot. That means the downscaled ratio, that's what it's called, means the neutrons that have lost energy, normalized to the 14.1 MeV neutrons, are measured for the rho R, or for the area density of the fuel. And finally, the gamma ray history spectrometer is a Cherenkov detector. It tells you for how long a DT process is being produced, and it tells you the lifetime of your detector. So let's just go quickly through them. This is a neutron activation. It's pretty much the chromium and copper foils, and neutrons activate them, the end-to-end process, and then you have the chromium 89 or copper 62, which you can take out and you can count them in a separate lab and know the total neutron yield. This is a neutron time of flight detector. If the temperature is high, you produce fast neutrons, and fast neutrons arrive early compared to a low temperature implosion, and you get a temperature measurement. This is an MRS detector, which gives you a measurement of the spectrum that has been produced. What's happening is you produce a neutron in your implosion, and you hit a CD foil that is sit next to it. You knock out a deuterium. Most of the energy is actually of the neutron is being transferred to the deuterium And now the deuterium, though, is charged, so you can use a big magnet to measure the spectrum, and you actually do this, and you can measure the downscatter ratio. That means that the neutrons that have lost energy by scattering in the fuel shell versus the primary neutrons. And then there's a gamma ray history detector, which is a Cherenkov detector that tells you that in this case, fusion processes are going on for hundreds, maybe 200 picoseconds. All right, so having said all this, so you look at how did the early shots perform. What's plotted here is the fuel rho r. That means the downscatter, the inferred area density from the downscatter ratio measurements. And the first experiments had fairly low rho r, but as we learned more and more, did several tunes, the rho r was actually going up all the way to the place where people thought alpha heating and ignition will set in. And let's go through some numbers. So this is, I told you the rho r is roughly, in this experiment, over a gram per square centimeter. This is this number. So you can now look at the ratio of the primary neutrons and the downscattered neutrons, that means those that have lost energy. This one tells you how big the fuel is. This one tells you how big the hotspot is. So the difference tells you the shell thickness. So we looked into that. So this is, those numbers are shown here. Now you can multiply those, and you get a density in this case of 550 gram per cc. So not quite 1,000 gram per cc, but close. So we look into, this gives us an electron density of 10 to the 26 electrons per cubic centimeter. That means highly compressed material. And from that, you can go into the textbook and calculate the Fermi pressure. And you see right away, the pressure here in this implosion was 80 gigabar. So this goes on for 120 to 150 picoseconds. That means the p tau was 10 atmosphere per second. This is the pressure. We arrive at this pressure by looking at the conditions of the shell. Now we can also look at the pressure by looking at the hotspot. The hotspot emits X-rays, and this is primarily through Bremsstrahlung, which scales like rho squared times temperature. So we know the temperature from our NTOF measurement, and we also know the density from the neutron yield. So we can combine these two numbers and get pressure through NKT of 92 gigabar, which is close enough. So this gives p tau of 12. So this implosion tells you right away that the pressures are high. They're not quite there, but they're much higher than previous fusion experiments that have been gone at actually the magnetic fusion or other laser facilities. So a plot like this was made by Riccardo Beddi with data from Friedberg at MIT, and it shows you how the pressure time product has increased and has scaled with higher temperature plasmas. That means with better and better plasma devices that have come online over the last century. And let's zoom in here to see anything. So this is, you see more D3D. Here's actually JET, the biggest tokamak fusion device in Europe. This is the projected point for ITER, and this was the previous Omega laser data point, and here was our first shot on NIF. And then all the other shots came out here. But you can see, compared to simulations, those pressures or p tau products were high. They actually exceed those that have been predicted for ITER, but they were not close enough. So predictions from simulations have shown that these p tau values will still need to increase by a factor of 3. And of course, people have jumped on that result right away and has published in Scientific American. I think you've also seen press about this in Nature and Science. Fusions falls dawn, and there was lots of talk in Congress and the Senate to shut down NIF. So only after like 1 year of experimentation. But shortly thereafter, things started to take off. So that was, and what is shown here, I show you the fusion yield for various shots. And the Fusions Falls Dawn article came out sometimes here, and just a few months later, a new result or new campaigns have started in, and all of a sudden the fusion yields have gone up significantly, over 25 kilojoule, and a big fraction of the fusion yield is due to alpha heating. That means more energy comes out than was put in. The blue indicates how much energy was needed to assemble the fusion plasma, and the red is the surplus to alpha heating. So what does it mean? How was that accomplished? What people have done, they've changed from a so-called low foot implosion to a high foot implosion. And the high foot implosion is just much more stable. That means those are calculations of instabilities, and a high foot implosion doesn't show instabilities, Rayleigh-Taylor instabilities on the fusion capsule. So what has changed? So only a very small change in laser power resulted in much improved performance. That means the laser foot has changed by this much. The peak power has not actually changed at all, but the timing of the various power rises in the laser pulse have changed somewhat. So that small change made a big difference. So what I take from this is that this is just the beginning of fusion research on NIF, and actually there's much more to gain by better understanding. So here's this picture again, the total yield versus compression yield. You can see that the total yield is actually taking off compared to the compression yield. And this is probably right now the state of the art. So this is the total yield. This is the energy required for ignition. The experiments show that right now it is possible to get 25 kilojoule total yield. However, in order for alpha heating to not only just heat the plasma, but in order to launch a nuclear burn wave to the fuel that surrounds it, one needs probably a yield of the order of 100 to 200 kilojoule. And in that case, alpha heating will set in, and big fusion yields will be the result. So this is now a factor of 4 to 5 in yield from the implosion that one still has to get out of the system. All right, so how will that be done? So one leading candidate for why it is so hard to make progress in capsule implosions is due to the fact that Rayleigh-Taylor instabilities are a big player. What this means is that you have material on the outside, which is a ablator, which is supposed to be gone. But as you implode, some of the material actually has been pushed all the way through into the hotspot. And this is high Z material, it's carbon, it's radiating energy away, it quenches the hotspot, it cools the hotspot. And those are simulations that were done by my colleague Bruce Hamill. This is there's an ablator here in green. It's a different material than what was used in the experiment, but it shows you in principle what's happening is as you implode the system, the outer material can be pushed into the hotspot plasma. And on the other hand, the implosion can also be stable. And the difference here is just a factor of 3 in conductivity. Now remember, those are high energy density science conditions. So nobody knows what the conductivity is. And for that reason, we've gone out there to do a science experiment to actually find out what is the conductivity in these plasmas, what are the growth rates for Rayleigh-Taylor instabilities, and then with that knowledge define or simulate implosions that actually work and field them later on NIF and other fusion devices. And for that purpose, we have developed a science program at the Linac Coherent Light Source, which is up here, up on the hill at SLAC. And this is our 3-kilometer long accelerator. And LCLS uses the last 1 kilometer to accelerate electrons to 14 GeV. And then they go through an undulator producing X-rays, and those X-rays will be transferred to the near and far experimental halls. And we do our experiment in the far experimental hall in the so-called matter in extreme conditions end station. We fire the X-ray beam into that end station, and we interrogate plasmas in the high energy density physics regime. So the way to do this, we do X-ray scattering. This is a wavelength resolved scattering. This is a spectral resolved scattering example. And we've actually, in order to make our experiments work, we've actually gone to a so-called self-seeding regime, which was actually new just when I arrived, and we were the first ones to test it in an actual experiment, and was extremely successful, partly because it has the record peak brightness. That means lots of photons, X-ray photons, at a very small energy bandwidths. And that was needed for us in order to resolve plasmons. So this is a standard or SASE spectrum coming out of LCLS. It produces a broadband emission signal, and when you look into forward or backscatter, one can hardly distinguish the two scattering signals. However, with the seeded beams, you have now a narrow X-ray bandwidth, and in forward scattering, one sees nicely a plasmon coming up, And that plasma actually tells us the compression of our system. We use laser beams to compress them. And it can also measure conductivity. So I just want to show you a few highlights here. This is one of the first results where LCLS has determined a high pressure phase diagram, in this case of aluminum. We've been able to succeed deriving a total pressure in our compressed system versus mass density. And what we can see is, first, you have a compressed solid. And you see, this is those are back peaks. And as you're compressing the solid, the back peaks shift to higher angles, higher wave numbers due to the Bragg conditions. So one can directly track the compression by looking at the Bragg peak, how it's shifting out. That means you're walking up this way. At roughly 1.4 compressed material, in addition to the shifted Bragg peak, we also observe a very broad underlining scattering signal. This is called the liquid peak, and it's an anion correlation peak. And as you compress further and go to higher pressures, the material is completely melted. There's no solid left. It's just a dense plasma. And we see a broad anion correlation peak shown here. And then we have actually shock waves that can collide. And as the shocks are colliding, the densities increase further, and the signal moves further out to even higher scattering angles. So with LCLS as a precision tool, we can now directly determine how a material will go through phase space and through what phases it will visit. All right, so we've then gone on and measured directly material strength and ionization. Because for reason of time, we'll skip on a detailed explanation here, and want to point out to our efforts to join in with the community and really to grow the science at the Matter in Extreme Conditions end station at LCLS. So we've had a high power laser workshop last year, and actually a new one is just announced today, October 7th and 8th, 2014. We will be here actually on just a few hundred yards from this building. And the goal is to bring in the community to really tell us what is the direction we need to take, where's the best science, and how do we take best advantage of the new instrument. And the first workshop was focused on high power laser matter interactions. We had all the experts there. We had experts on high power laser science and technologies, and we defined the new directions that we want to go to. And this is partly motivated because many MEC experiments have just been done in a very small regime in phase space, namely at about 1 gram per cc, which is close to solid density. And with the advent of a high power laser system that we have now begun to commission at MEC, we can now access a huge parameter space in MEC experiments with LCLS. In particular, we can study material at high temperature fusion plasma conditions. We can study energetic particle generations, MeV proton beams, GeV electron beams, and we can do astrophysics experiments, collision shock experiments, and QED experiments. And here an example of how we want to progress with this. So we want to study fundamental laser plasma interactions. We want to continue to study high pressure systems, shock compressed matter, and we want to perform laboratory astrophysics, self-organization in plasmas, and the production of Weber instabilities, formation of collisional shocks, and we want to study the physics of the origin of cosmic rays. So in order to accomplish this, of course, I told you we have to have a 200 terawatt laser commissioned and operational. That's going to happen soon. However, we feel that it will be important that we continue to upgrade the laser capabilities at LCLS, and we have a proposal to do so. And one of them is to put a high power pump laser just on top of the hill where the MEC end station is. We get the pump laser down, and then the high power laser meets the LCLS X-ray beam to do novel pump probe experiments and to study high energy density physics. And that proposal is very timely. As people know, high power lasers are now taking off all over the world. So there's a 10 petawatt laser system being built in Europe at Eli. I've actually been invited end of June to go there. So they're building a 10 petawatt laser, 1 petawatt laser, 10 kilojoule laser, all in one place to study high energy density physics. There's a so-called high wave end station at the X-FEL laser facility, which X-FEL will have similar capabilities as LCLS and LCLS2. And they're going to have a 200 terawatt laser next to it, but this 200 terawatt laser will shoot at 10 hertz. So once they're going to start to operate, they can do a lot of physics. And here at SLAC, we will need to have a new building or new shielding and new infrastructure. And if we can put it all in place, we will have a high access option to the end station. That means every time we can fire the laser, we will ask for an X-ray beam to have a pump probe experiment. All right, and with this, I want to skip over this. I now want to thank you for your attention. I want to summarize here. What needs to happen? I think the first step is really to continue developing our understanding of matter in extreme conditions. That means we will do LCLS experiments of fundamental science in high energy density physics. We want to have a high power laser driver and measure important parameters for fusion, such as conductivity, such as ionization. And down the road, what will be needed is that fusion will have to be demonstrated in a single shot experiment in the laboratory. That means the alpha yield performance will have to still increase by a factor of 10, which in my opinion can be accomplished with improved physics understanding of materials in high energy density science regime. The total gain will have to be between 50 and 100 with laser fusion. I showed that at the beginning of the talk. And one can even talk about advanced fuels once this is accomplished. That means deuterium-only fuels or dihelium-3 reactions. And of course, once this is demonstrated, the next step would be to develop an efficient driver and target technology, so that right now a NIF laser can do 3 shots a day. That has to change to like 10 shots a second. And the technology for targets will have to be developed in order to do that. And of course, diode pump lasers will have to be developed in order to make this quantum step. So in many ways, fusion research is still a fundamental science program. But time is running out. The million ton CO2 limit is coming closer every day. And even coal will run out eventually. So in that sense, although it is fundamental science, we better get on it. And with this, I'd like to thank you for your attention and take your questions.
Okay, talk is open for questions.
Having been in the plasma physics group at Stanford in 1961, the agreement then, amongst all the professors involved, was that fusion would be 20 years later. We had our reunion in 2011, 50th reunion, and everybody was there except for one. And the agreement then, after some drinks, the faculty club, was it's 30 years ago. So, given you've got a factor of 10 there, and you've got the laser problem, and you've got to do 10 shots a second, what is a realistic prototype power?
All right, so of course I've seen this stuff before, but you know, I just want to give you one thing. So this is US fusion research, right? It's $500 million per year since 1975. 30 billion total. That's a joke, right? That's a joke. So if you think about what German consumers are paying now, they're paying $100 billion a year in order for the electricity.
Right. But that's
so without any money in this field, there's, you know, it's going to be another 30 years away, of course.
Right, but you can do what the French did.
So, no, you can't. Well, you can. We don't see. I don't want to go into an energy argument in this talk.
Done what the French did.
What I'm telling you, this is a fundamental science program. Progress has been made, which is undisputable. Right. And the question is, can you make more progress to convince politicians and the society to put more money into the field? And I believe it's up to the researchers to deliver on making more progress.
For years.
Yeah, to follow up on this theme, which is not to say scientific research shouldn't go on, but let's say you were somebody who was looking at global energy issues and the urgency of moving energy technology away to more renewable technologies, and you said, gee, I want to give advice to a politician or fund science and technology developments. What fraction of the budget that's going into energy research do you think should go towards fusion, whether it's inertial confinement or laser-driven, what fraction should go towards development of nuclear reactors, what fraction should go towards improving the efficiency of our energy economy. In other words, if I have $1 to invest, do I do better investing in efficiency on the end use or investing $1 in fusion research? I'm curious, in your portfolio, where you would put your dollar investments.
All right. So having grown up in Germany and having seen how people have set their money into renewables, in my opinion, it's a total failure. And so that's where I would not put my money. I would put money into CO2 sequestration because I think if you don't do this, this planet is going to die very quickly. That's where I would put my money. And I would put it into fusion because coal is running out as well. So you're asking me, I would continue to push the sciences. I would continue to push fusion research. I would continue to try to tackle the atmosphere problem. And I would try to get away from a CO2 economy as fast as I can.
Why are you ducking the discussion of nuclear? It seems to me that is it political? What France does pretty well with it. What's up?
Well, so in preparing this talk, of course, I was thinking about should I get into a big discussion on nuclear power. I looked up, the resources that are available, how much uranium is left, and then can we go to thorium down the road? How many hundreds years can we do? Maybe a few hundred years.
10,000. 10,000 years worth of thorium. You really have to be accurate about
So
it.
you can do thorium.
Right,
you can try that.
Okay, and
So-
the Indians are doing it.
Right. So the question is.
Chinese are doing
No. We can have a nuclear fuel discussion,
it.
and
That's what we should
I
have.
can give a. Well, you don't have to come to this talk, right? So if you don't want to listen to what I have to say, you can leave the audience. So nuclear power is definitely a step that where actually would also put some money. But is it acceptable? Can you convince the society to go that way? I have some strong doubts. And the reason for that, I showed you, I think, in the very beginning. So now I have to go back all the way. Because there's one way to be smart about stuff and to tell people what to do, and another thing is what people are doing, right? So if we go to that place, let's see. Here it is. See that nuclear? The tick is down. That means despite all of us saying, yes, nuclear can help, in the end, that's not what people do. In the end, that's not where the society go. Where the societies go. That's not where China is going, that's not where India is going. That's what happens. People invest into coal, gas, and oil.
You haven't been kept up with what's going on with this.
Okay, let's get some questions from this.
That's an interesting.
But this is a slide.
We're trying to get students.
I know.
Okay, okay.
Okay, I was going to ask a question about the instrumentation. It seems like there's a lot of pretty neat instrumentation you have hanging off these devices, each of which could take several PhDs, I gather, to make them work. How well is the science funded for that level of things? Because instrumentation makes a big difference in what you can get out of your experiments.
Yeah, so much of the nuclear diagnostics actually being developed together with researchers at MIT, at the Laboratory of Laser Energetics, and there are many students actually involved in this sort of research. So if you have interest and if you have students who want to get engaged, this is a perfect way to get in. So there are grants around. There's student grants and postdoc grants around to have people come and work on these diagnostics.
So a more mundane question, perhaps. So let's assume that you can make stuff work pretty well.
Talk about the DT reactions versus the deuterium only, since there's a lot of deuterium, but there's not so much tritium around. And, you know, where do you go if you can really make this stuff work? I mean, what do you use for fuel, really?
Right. So initially, DT is the best. The best mixture because the cross section is the highest.
Sure, yeah.
So, and what people are saying, you put a lithium blanket in your target chamber and you breed tritium.
Oh, okay.
That would be the easiest way to deal with the lack of tritium. However, the DD cross section is actually not that bad either. So people think about advanced fuels. That means maybe you trigger it off with DT, but then have deuterium around. There's also D-helium-3 is also a good technique, and there's actually probably one of your famous colleagues that actually proposed to go to the moon to harvest helium-3 from the moon. So that people are thinking about the fuel question, yes.
Do you by any chance know how difficult it is or what the process is like to extract the deuterium from seawater?
So at the moment, there's no deuterium problem. so it's not that hard. So I think people do it with diffusion, and actually it goes all the way back to the Second World War, where people have extracted deuterium from in Norway. Exactly, there's a famous plant, and people were afraid that the Germans would develop a nuclear bomb using deuterium as a moderator. So actually, that hydro plant there was an attack on it to take it out of business. So with hydro plants and stuff, there you can do it. Yes. Okay.
I noticed that your prices there are from 2002.
Yes.
I believe solar's come down appreciably since then.
Possibly.
Yeah, not possibly, actually.
But it hasn't. But it doesn't make a difference in the energy budget. If you look at the total, where you get the total power from, it doesn't make a difference. And the reason why that's the case, if you can go through bottom up or top down science, and you can think about how much land mass you need in order to make solar work, and you need huge amounts of land. You need actually for the United States, you need the whole state of Colorado to make it work. And I'm not saying that may be possible down the road, but it's not possible now. But maybe that's also one direction where we will be going.
I'm just curious about the price of deuterium. It used to cost about the same as beer, but now it costs about $400 a kilogram. What's going on with that?
I actually don't know. I haven't followed up on the price of deuterium lately. Sorry.
You said once you create these high energy neutrons, you transfer that energy to a lithium blanket?
Yes.
And so I guess my question is there a lithium supply issue, or does that lithium?
No, lithium. There's plenty of lithium on the planet. It's one of the most abundant minerals. Actually, the process is exothermal, right? So what's happening is you multiply the energy production by factor 1.2 as you capture the neutrons in the lithium. It's actually a good thing to do.
Okay, let's thank Siegfried again.